Greetings all. In this video, as the title indicates, I would like to speak a bit about fuzzy set theory and fuzzy logic. I would like to give a very basic, brief overview of the fundamentals of fuzzy set theory, and then I would like to share an interesting insight that I recently had into the intuitive basis of generalized operations, intersection, and union in fuzzy set theory and how they relate to those operations in classical or traditional set theory. For those unfamiliar with the topic, fuzzy set theory is an alternative set theory framework originally proposed by Lofty-Zadeh. I believe, I know I'm butchering the name. My apologies, I don't have the IPA up in front of me at the moment. Um, but Zadeh originally published the paper which established the groundwork for fuzzy set theory in 1965, and ever since it's been of interest to numerous fields, numerous disciplines, and it's been of use to numerous disciplines such as electrical engineering. Zadeh, an electrical engineer by trade, published his paper from that standpoint originally. Cognitive linguists, for instance, which cognitive linguistics is my field of expertise and of interest, and is the reason for my interest in fuzzy logic and fuzzy set theory as a result of research that I'm currently conducting in cognitive linguistics and conceptual metaphor theory, um, and numerous other fields in pure and applied mathematics, philosophy, and so forth. Fuzzy set theory is so incredibly useful because it provides a framework through which to describe categories while preserving gradations thought to be cognitively real in the mind and which are indeed common in reality, in perceptive reality. Most categories do not conform to the notion of a classical set in reality. The category of tall people, for instance, I mean, height, weight, all sorts of these sorts of attributes, age, these indicate gradations. Um, Social status, the list continues on. Gradations are extremely common in reality, and fuzzy set theory provides a framework by which to describe them. If you'll recall, in classical set theory, um, for those who may be unfamiliar with fuzzy set theory, in classical set theory, elements are assigned a membership value, a binary membership value, either 0 or 1, which indicates membership in a set or membership or the lack of membership in a set. So, for instance, if an element X was assigned the membership value 0 in the set A, then that would indicate that X is not a member of A. If it was assigned the membership value 1 of A, it would indicate that X is in A. And there are the basic operations of intersection, union, and so forth, complement, and so on. Well, in fuzzy set theory, by contrast, elements are assigned a unique real value, a real number value between 0 and 1 by a membership function which indicates the degree of membership in the fuzzy set. So in this sense, just intuitively fuzzy, the adjective fuzzy to describe fuzzy set theory um, seems to suggest a framework in which gradations exist and are preserved. It's something is either in or not in a set in classical set theory, whereas in fuzzy set theory there are gradations of membership, essentially. Well, I recently, while pondering the nature of operations in fuzzy set theory, I recently um, had an interesting insight, which may be immediately obvious to some, may be of interest or assistance to others, so I thought I'd share it here for your benefit. As Zadeh originally defined them, the operations in fuzzy set theory do not seem particularly intuitive, at least to me. Um, I have had some formal mathematical training. They were not immediately intuitive. He defined intersection to be the value of an element in, if you consider fuzzy sets A and B, the value of an element in the intersection, um, assuming that A and B are not disjoint, is defined by Zadeh to be the minimum of the membership values in A and in B, respectively. And the value of X in the union of A and B is defined to be the maximum of the membership values, again, respectively in A and B, where A and B are fuzzy sets. This doesn't necessarily appear to be immediately intuitive. Um, the union, the definition for union, um, just beginning from there seems perhaps somewhat intuitive. The maximum of values, if union is obviously a larger set, And so the membership value, the maximum. But if you consider, even though these don't seem necessarily intuitive, if you consider in classical set theory, you'll find that they actually apply and that they're a generalization, as they originally stated from classical set theory. Um, in classical set theory, consider two sets, A and B, and an element which are not disjoint, and an element x. Um, the value of x is, suppose that x is a member of A, but not a member of B. Well, then the value of x in A intersect B, or A and B, is 0. Well, the value of x, it restated in the binary terminology, the value of x in A is 1, because it is a member of A, and the value of x in B is 0. It is not a member of B. And so therefore the value of x in A intersect B, or A and B, is 0. That is the minimum of those two values. Um, that seems sensical, intuitively, that if it is a member of one of the sets and it's not a member of the other set, then it cannot be a member of both sets simultaneously, or in other words, it cannot be a member of the intersection. Now consider the value of x in A union B. Well, the value of x in A union B is 1. It is a member of A union B, as union is defined in classical set theory. Um, and that is the maximum of the membership value of x in A and B. Of 0 and 1. The maximum of 0 and 1 is 1. So this is intuitive. This is perfectly sensical. And Zardea simply generalized it to fuzzy sets.